Welcome to a crucial module on building robust applications, exception handling, assertions, and logging. No matter how well you write your code, things will eventually go wrong. A file might be missing, a user might enter unexpected data, or a network connection might drop. This module teaches you how to handle these failures gracefully without crashing your program. 1. The need for error management. When a runtime error occurs, Python raises an exception. If this exception is not caught and dealt with, the program terminates immediately, leaving the user with a confusing traceback message and potentially leaving resources like open files unclosed. Handling exceptions is key to user experience and resource cleanup. 2. The 3 tools of robustness. We will focus on 3 tools: exception handling, logging, and assertions. We use try, except, else, and finally blocks to intercept errors at runtime, prevent crashes, and provide a controlled response, such as retrying an operation or alerting the user. We use the logging module to record events that happen in your application, not just errors, but also warnings, informational messages, and debug data. Logging is crucial for understanding what went wrong in a deployed application. We use assert statements to confirm assumptions about the state of the program, particularly during development. If an assumption is false, the program halts immediately with an assertion error, which helps catch internal logic bugs quickly. To summarize, mastering these techniques separates reliable, production-ready code from simple scripts. Our next lecture, 22.02, Exception Class Hierarchy. See you there. Welcome back. Before we start handling exceptions, we must understand how Python organizes them. Exceptions are organized in a hierarchy, just like classes in OOP, allowing us to catch errors at different levels of generality. 1. The root of all errors, base exception. At the very top of the hierarchy is base exception. All system exit messages and exceptions inherit from this. Generally, you should never catch base exception because it includes events like system exit and keyboard interrupt, which are usually meant to terminate the program. 2. The main branch exception. The most important branch is exception, which inherits from base exception. This is the base class for all non-fatal exceptions, the ones you should usually handle with your try-except blocks. If you write except exception, you catch nearly all common runtime errors. 3. Common runtime exceptions. Many common errors you encounter inherit directly or indirectly from exceptions. Let's look at a few common examples and how they relate. For example, zero division error inherits from arithmetic error. Similarly, trying to access a non-existent dictionary key raises a key error, which inherits from lookup error. Catching the base class, like lookup error, means you can handle both key error and index error with one block. These are very frequent. Value error occurs when an operation receives an argument of the correct type but an inappropriate value, such as converting the string hello to an integer. Type error occurs when an operation is applied to an object of an inappropriate type, like adding a string to an integer. 4. Why the hierarchy matters. Understanding the hierarchy allows for specific error handling. When an exception is raised, Python searches for a matching except block. If it doesn't find a direct match, it looks for an ancestor class in the hierarchy. This means that if you catch lookup error, you automatically catch any specific error that descends from it, like key error or index error. To summarize, knowing the hierarchy allows us to write concise yet comprehensive error handlers. Our next lecture, 22.03, Handling Exceptions. See you there. Welcome back. Now that we know what exceptions are and how they are structured, let's learn the fundamental way to manage them. The try-except block. This structure allows us to wrap dangerous code in a try block and provide recovery logic in the except block. 1. The basic try-except structure. The try block contains the code that could fail. If an exception occurs during execution of the try block, the program immediately stops running the try block and jumps to the corresponding except block. Here, the except zero division error block specifically catches a division by zero error, prints a friendly message, and allows the program to continue execution instead of crashing. 2. Catching multiple specific exceptions. You can chain multiple except blocks to handle different types of exceptions. Python checks them sequentially. If the input is not a valid number, value error is caught. If the input is 0, zero division error is caught. It's best practice to be as specific as possible to provide accurate error handling and feedback. 3. Catching exceptions by type tuple. If you want the same recovery logic for several different exceptions, you may list them in a tuple inside a single except statement. This makes your code cleaner and avoids repetition, though the error message here is less specific. 4. Accessing the exception object. We can capture the actual exception instance using the keyword as. This assigns the error object to a variable, usually eq. This allows us to print the specific error message provided by Python, which is useful for debugging and detailed logging. To summarize, handling exceptions is essential for reliable code. Our next lecture 22.04, using finally. See you there. Welcome back. When dealing with resources like files or network connections, it's crucial to ensure they are properly closed, regardless of whether the main operation succeeded or failed. This is the primary purpose of the finally block in Python's exception handling structure. 1. The role of the finally block. The code inside the finally block is always executed before the try-except statement finishes. This makes it ideal for cleanup tasks, ensuring system integrity and preventing resource leaks. 2. Example, file handling with finally. In this example, we attempt to open a file. If the file is found, the try block executes successfully. If the file is missing, the file not found error is caught. But whether the file is read successfully or the exception is caught, the code in the finally block runs, guaranteeing the file, if opened, is safely closed. This prevents the file from remaining locked by the system. 3. Execution flow demonstration. Let's trace the flow in two scenarios. If the file exists, the order is try block runs completely, then the finally block runs. If the file is missing, the order is try block fails immediately, the except block runs, and then the finally block runs. The cleanup is guaranteed. To summarize, always use finally for resource management. Our next lecture 22.05. Else. See you there. Welcome back. We've covered try, except, and finally. Now let's look at the often overlooked but very useful component, the else block. This block helps you write cleaner code by clearly separating the code that depends on the try block succeeding from the main try logic. 1. The condition for else. The else block is executed only if the try block runs completely without raising any exceptions. This makes it an ideal place for code that processes the successful result of the try block, but does not need exception handling itself. 2. Example: successful calculation. In this example, if the division in the try block succeeds, Python skips the except block and executes the else block, printing the result. This separates the error-prone step, division, from the success processing step, printing the result, making the code easier to read and maintain. 3. Example: handling failure. Now, if we introduce a zero division error, the try block fails. Python immediately jumps to the except block. The else block is completely skipped, confirming that the success-dependent code is never executed when an error occurs. 4. Relationship with finally. It's important to remember that if the else block is present and runs successfully, the finally block runs immediately after it. If an exception is caught, the except block runs and then the finally block runs. The finally block always executes last. To summarize, we've now covered the complete structure, try except else finally. Our next lecture 22.06, create and raise custom exceptions. See you there. Welcome back. While Python provides many built-in exceptions like value error or type error, sometimes you need an error type that is specific to your application's logic. In this section, we'll learn how to create and trigger our own custom exceptions, providing clearer feedback to users and developers. 1. Creating the custom exception class. Creating a custom exception is simple. Define a new class that inherits from the base exception class. We call ours insufficient funds error. By inheriting from exception, it becomes a fully recognized exception in the hierarchy. We override the constructor to accept specific data, like the current balance and the attempted amount, and we override the _str_ method to provide a detailed, readable error message. 2. Raising the custom exception. To trigger the custom exception when a business rule is violated here, when the withdrawal amount exceeds the balance, we use the raise keyword followed by an instance of our exception class. When raise is executed, the function immediately stops, and Python begins searching up the call stack for a matching except block. 3. Catching the custom exception. Finally, we use a standard try except block to test the functionality. Because our function violates the rule, it raises insufficient funds error. The except block specifically catches this custom error, and we use the exception object, e, to print the detailed, custom error message we defined earlier. To summarize, custom exceptions make your code much more professional, reliable, and easier for others to debug. Next, we will solidify this concept by working through a few more comprehensive examples of creating and managing custom exceptions in different scenarios. Our next lecture 22.07, More Programs Custom Exceptions. See you there. Welcome back. To solidify our understanding of custom exceptions, we will work through a more comprehensive example using a data processing scenario. This program will require us to define a small hierarchy of custom exceptions to handle different types of data validation errors. 1. Defining an exception hierarchy. It's often helpful to create a base custom exception, like data validation error that inherits from the main exception. Then we create more specific exceptions that inherit from our base class, such as missing field and invalid value. This structure allows us to catch all data errors generically or handle specific errors individually. 2. Function with multiple validation checks. Our process_record function now uses these exceptions. It checks for a missing name, then a missing age. Crucially, it then checks if the age is a valid positive integer. If any of these business rules are violated, we use the raise keyword to interrupt execution and signal the precise error condition using the appropriate custom exception. 3. Catching the hierarchy. We test two scenarios. In the first example, we catch the specific missing field exception. In a larger try-except block, you may catch the generic data validation error to handle all derived errors with a single handler. This flexibility, enabled by the exception hierarchy, is extremely valuable for complex systems. Remember, always catch the most specific exceptions first. To summarize, we've now learned creating, raising, and handling specific custom exceptions. But what happens to the errors we catch? We need a system to record them. Our next lecture 22.08, Logging in Action. See you there. Welcome back. We've learned how to gracefully handle immediate errors using try-except. Now we shift our focus to professional application monitoring, logging. Instead of using simple print statements, the logging module allows us to record events with crucial context, timestamps, and severity levels. 1. Why use logging? Unlike print, logging allows you to control which messages appear based on severity, directs messages to various destinations like files or network servers, and automatically includes metadata such as the timestamp, log level, and the file that generated the event. 2. The 5 log levels. Python defines 5 standard severity levels, from least critical to most critical. Understanding these is essential for configuring your application. The levels are debug, info, warning, error, and critical. Debug logs are for internal deep dives, info logs for normal operations, warning for minor issues, and error or critical for failures. 3. Logging to the console. To get started, we import the logging module. Notice that when we run this code, by default, we only see warning, error, and critical messages. Info and debug messages are silently ignored. This is because the default threshold for Python's logging system is set to warning. 4. Default output format. The basic output format includes the level, the logger name which is root by default, and the message itself. This already gives us more context than a simple print statement. To summarize, we've begun using the logging module and identified the default behavior. Our next lecture 22.09, Logging Configuration. See you there. Welcome back. In the previous section, we saw that Python's logging defaults to the warning level, ignoring debug, and info messages. To make logging truly useful for development, we need to configure it. We do this using the logging.basicconfig function. 1. Setting the log level. By passing level equals logging.debug to basic config, we lower the threshold. This tells the logger to process all messages at the debug level and above. Now, when we run the code, the previously hidden debug and info messages appear in the console. 2. Formatting the log output. The default output format is basic. We can customize it using the format argument. To do this, we use specific log record attributes, which are placeholders that Python replaces with actual data, such as the time or the log level. In this example, we define a format string. %AskTime s inserts the time, %LevelName s inserts the severity, and %message s inserts your text. This structure makes logs much easier to read and analyze. 3. Logging to a file. In production, you rarely watch the console. You need logs saved to a file. We achieve this by adding the file name argument. We also set file mode to W to overwrite the file each time the program runs, or to append to the existing file. Once this is set, logs will go to the file and will not appear on the screen. To summarize, proper configuration turns logging from a simple tool into a powerful monitoring system. Our next lecture 22.10, Log Exceptions. See you there. Welcome back. When your application crashes in production, a simple error message like "File not found" may be not enough. You need the full story, the traceback, which tells you exactly where and why the code failed. Today, we will learn how to configure the logger to capture this vital debugging information automatically. 1. The problem: missing context. If we use a standard logging.error call inside an except block, it only logs the text string we provide. The crucial information, the stack trace showing that line 4 caused a 0 division error, is completely lost. This makes debugging difficult. 2. Solution 1. Using exe_info equals true. To include the traceback, we add the argument exe_info equals true to our logging call. Now, the logger automatically looks up the current exception information and appends the full stack trace to the log message. 3. Solution 2. Using logging.exception. Python provides a shortcut method specifically for this purpose, logging.exception. This method logs a message with the level error and automatically sets exe_info to true. It is the preferred, cleaner way to log errors inside an exception handler. To summarize, always capture tracebacks when logging errors. It turns a mysterious failure into an obvious fix. We have learned exception handling and logging. The final tool in our robustness toolkit is Assertions, a powerful way to perform sanity checks during development. Our next lecture 22.11, Using Assertions. See you there. Welcome to the final section of our module on robust programming. We have covered runtime errors with exceptions and historical logging. Now, we introduce a tool for debugging internal programming logic during development. Assertions. Assertions are sanity checks. They test if an assumption you made about the code state is true. 1. The assert syntax. The assert statement takes a condition and an optional message. If the condition is true, nothing happens, and execution continues. If the condition is false, Python raises an assertion error, immediately stopping the program and displaying the optional message. The failure of an assertion indicates an internal bug that needs fixing, not an expected runtime event. 2. Assertions versus exceptions. This is a critical distinction. Assertions are for programmers and should only check for conditions that should never happen if your logic is correct, such as checking if a variable is not none after an operation guaranteed to return a value. Exceptions are for users and handle expected runtime failures, like a file being missing or bad user input. 3. The dangers of assertions. Assertions can be globally disabled when Python is run with the optimization flag -O. When disabled, Python completely ignores the assertion statement, including any side effects. Therefore, you must never include essential code inside an assertion condition, such as calling a function that performs a critical calculation or I/O. To summarize, use Jassert to catch bugs in your own logic quickly. Okay, you have now learned exception handling, logging, and assertions, the core tools for writing robust Python applications. Okay, we are going to the next section, section 23. Our next lecture is 23.01. Introduction. See you there.